So the next bit we're going to look at is Thomson's charge to mass experiment. And as I said, if this explanation gets a bit too long, we'll cut it into two parts. So Thomson's charge to mass experiment, we're going to evaluate and assess his actual model. We're going to look at how he came up with the model. Okay, and this is with the tubes and everything we have here. Now, you might remember him. He's the guy who came up with the idea of the plum pudding model of the atom. So you can see these little raisins here. That's all the different negative charges. And then all of this other bits here, that's the positive cloud, if you like, is how he explained it. So let's look at how he sees this. The plum pudding model. If you actually see sort of the similarities of where he's getting at. Like I say to a lot of people in the lessons, these quotes are just for comedical effect. He didn't actually say that. Okay, so the charge to mass ratio, and I'm going to show you a little simulation here, is to investigate the effect of electric fields and magnetic fields on the moving charged particle. Okay, so if we just look at the equipment, we have the cathode, thermic cathode. So what that actually means is we're going to heat up the cathode, and remember what I said earlier, heating up the cathode will release more electrons. This will go through the anode. Now the anode is positively charged, so there's going to be an attraction force that's going to cause the electrons to accelerate through. That gives it an additional velocity, and depending on how we manipulate the charged plates and the magnetic field, we can cause movement of the electrons here, and then we can see the movement at the fluorescent screen. So we'll see the little dots. Okay, so I'm going to use this simulation here, the charge to mass ratio for an electron. Thank you to Tom Welsh and GeoGebra for this simulation, which is quite useful. So there's some nice numbers here. So that's what we're going to look at. Okay, so in 1897, a British physicist in the name of J.J. Thomson used the cathode ray tube to determine the mass to charge ratio of the electron. Remember, at this point, they do believe that the electron was a particle, so they wanted to know what was the mass, what was the charge that the electron had. So let's put it through the simulation. So the function of Thomson's cathode ray tube is to send the electron beam through here towards a particular target. Okay, the beam will pass through an area of both the electric field, so that's our electric field here, and then also a magnetic field, which is indicated by these gray dots. Okay, the electric field is created by a pair of charge conducting plates, so electricity is going to these two sides to make one positive, one negative. What we can actually work out is already it goes from down here to up here, so that would imply that this plate is the positive plate, this plate is the negative plate. Okay, so let's try and run it through, and we see that the electron kind of bends down like that. Okay, so what was he trying to do from this? Let's just look at some of the equations. Okay, so the equations in investigation or in inquiry, I'm going to look at these two here. This is from early in Module 6 and a bit of Module 4. So we know that the force applied on a charged particle by a uniform electric field, so if the electric field is constant, hence our charged plates, goes through this. If we want to know the electric field strength of the plate, we use this formula here, voltage divided by the distance of separation. Okay, and then we can also work out some other stuff with the magnetic field. These are the equations we're using here. This is from Module 6 as well. Okay, so first stage we already said we want to find we want to firstly make the magnetic field and electric field cancel each other out. Okay? So, running it through, just like that. So what I want to do is make sure this beam goes directly straight. Okay? Do the opposite. Okay, so as you can see here, around about 33 volts and a magnetic field of about 500 micro teslas, we can make the force of the magnetic field equal to the force contributed by the electric field. Once that happens, the beam goes directly across here. Okay. Remember, so the way the actual experiment is structured is the magnetic field is going to push the electron one way, the electric field is going to push the electron another way. If I can make it go directly straight through, meaning we've made the magnetic field and the electric field directly equal to each other, we can actually do some calculations to work out the velocity of the electron. So let's have a look. Okay. So the first thing is I want to make sure that the force of the electric field and the magnetic field are equal to each other. So EF is the force of the electric field, FB is the force of the magnetic field. Okay, EQE, that's the formula for force of the electric field. QVB is the force of the magnetic field here. If you're not sure, definitely look at your data sheet right now, formula sheet, to work it out. Okay, if I rearrange this, I'll know the common factor here is the charge of the electron. Okay, so I don't really want to know that right now. I just want to know how fast this electron is moving. Okay, so rearrange that, move B over. So V equals to the force of electric field divided by the force of the magnetic field. So if we have a look at what we have, the magnetic field, I said earlier, was about 500 microteslas, which is also the same thing as saying 500 times 10 to the power -6 teslas here. The next thing I need to work out is the strength of the electric field, which is not given to me. So I know that this here is voltage of 33. We know the distance is 5 millimeters. Okay, remember, electric field strength is given as voltage over distance. So the voltage is 33. The distance is 5 millimeters, so it's 5 to the power of, or 5 10 to the -3. So let's do some quick calculations. So we have an electric field strength of 6,660. So let's substitute that into our equation here. We get about 132,000,000. Is that enough zeros? Yes. Meters per second. Okay, so that's the speed of the electron there that we found. Okay, so let's get these calculations done. So the accepted value of this mass to charge ratio is that. We're going to talk about that in a second. Okay, so we're saying the velocity is around about that. The next bit we're going to do is work out the charge to mass ratio. This value will come in handy for it. Okay, so the next thing he did was turn off the electric field and only allow the magnetic field to be in action. Okay, so let's put it all the way down and run this again. Okay, so you see that pattern there. Now what you might not be able to see is this is a formation of a circular path. So if we have a circular path forming, we're getting centripetal acceleration. So what we're going to try and equate here is the strength of the magnetic force and centripetal force, and from that we are going to work out the charge to mass ratio of this electron. Okay, so what you see here, just had a little scribble here because the equations aren't correct, but because we have the centripetal force and magnetic force, they equate to each other to get this, we need to try and find the mass to charge ratio. So the end product, we want Q over M, so we're going to try and manipulate this equation to get that particular outcome here. So just write that out. QVB. So if I move velocity over, I get this equation here, 2 squared. They're going to cancel out where we only have one velocity, the other velocity disappears. So it's mvr equals to qb. Okay, then I'm going to move m over here, so it becomes vr, b moves along here, and then we get qm. Okay, so we know what the velocity was from the previous calculations, and we know what the magnetic field strength is. The only thing we need to know is the radius. So according to the simulation, the radius, again, to the calculations we have, the radius is 15.032 millimeters. Okay, so I'll write that down somewhere so I don't forget. Radius is equal to 15.032 millimeters. Okay, so let's do the calculations now. Alright, I'll also have the velocity value just so I don't forget. So I'm going to write these numbers down here. So the velocity is 132.00000 over the magnetic field strength of 500 microteslas times our radius, 15.032 10 to the power -3. That gives us an approximate value of 1.725 10 to the power of 11 coulombs per a kilogram. Okay, so moment of truth, time to see if that is the same value that the simulation gives us. So we go to the very end, and what do you have? Very close to the actual value. Okay, now if you want to readjust this to have electric field and magnetic field as the charge, this is the other way you can write it. So velocity is equal to E over B. So what that actually means is we just substitute here, E B squared R equals 2Q over M. And that's another formula you can use besides that. So that's how J.J. Thomson worked out the charge to mass ratio of the electron. So this is the final number he had. The negative obviously implies it's a negative charge. He actually found that this value was 1,800 times bigger than a hydrogen ion, what we now know is a proton. So he had two ways of thinking about this. Either the charge was a lot bigger, or the mass was a lot smaller. He came up with the idea that it was a lot smaller. Now this is how he did it. Okay, he actually changed the type of metal, so he changed the different cathodes up, and he still saw a cathode ray. Okay, so he still saw all the exact same properties, even though he kept on swapping the type of metal electrodes he used. This would imply a particular idea, is that these, if they are found in all different types of metals, then that means this is a subatomic particle of the actual atom, so smaller than the actual atoms of that piece of metal, and it's found in all different types of elements. He came up with the idea or reading of it being called the electron, and it's negative in nature, negatively charged, and it's also a particle. This is understanding. That's what he came up with all from his investigations. He won a Nobel Prize for it as well. And to conclude, he basically used these ideas to come up with the J.J. Thomson plum pudding model. The idea is very simple. You have a dent or a positive cloud of area of space, and that's the shape of your atom. Inside the atom, you have discrete charged negative particles called electrons, and then in all that other empty space, there are positive charges. So that was his idea, and the reason being is because atoms are neutral, so in order to balance it out, if we know that there are negative charges inside the atom, there has to be positive charges to balance it out. Spoiler alert, that's incorrect. But we'll go through that in a different lesson when we talk about Ernest Rutherford's model of the atom. But until then, these are your summary notes, and I'd just like to say thank you for sticking by and reading through. You are always welcome to come back and watch some other videos. Next one will be about Ernest Rutherford's contribution and Geiger and Marsden's experiment with the gold foil. But until then, thank you for coming to the classroom. I'll see you another time.